Now that you've learned the basic purpose of the various input and output sensors, it's time to take a look at them in greater detail. Probably the most important of the several key sensors we'll be discussing is the oxygen sensor. Although it's a pretty simple piece of equipment, no moving parts, without it, you can forget the whole 3C system. The oxygen sensor is the primary data sender to the ECM, which in turn helps the onboard computer determine that all-important air-fuel ratio of 14.7 to 1. As we mentioned in the first tape, this ratio is the crucial formula for the efficient operation of the modern automobile. The oxygen sensor is generally located in the exhaust manifold near the engine. However, you'll find a few cars where it's installed in the exhaust pipe, but this is the exception. When removing an oxygen sensor, remember it helps to start with a warm manifold. And if you need to replace an old sensor, always use a little anti-seize compound, and never more than 30 foot-pounds of torque when tightening. There are two types of oxygen sensors in common use. Basically, the only difference between them is whether the unit has one wire or two wires, or more technically speaking, whether the unit is externally grounded or self-grounding. To understand how the oxygen sensor works in the system, it isn't necessary to grasp all the chemistry and electrical theory. All you need to know is what goes on in the manifold and just what type of information the O2 sensor is sending to the ECM. Essentially, this is what an O2 sensor looks like in cutaway. Simply stated, the oxygen sensor compares the air inside the unit, which is fixed, to the air in the exhaust and relays this information to the computer. The tip of the O2 sensor is made up of zirconia dioxide. It's located inside the manifold, so it can sense the amount of air in the exhaust manifold. The outside and inside of the O2 sensor tip is coated with platinum, just like the catalytic converter. The inside of the sensor should also contain about 21% oxygen, roughly the same as atmospheric air. And to maintain this oxygen level, all the openings must be kept clean and clear. You'll want to be extra careful on the GM sensor with the silicon boot. The boot should not be shut down tight, or the air will not be able to get into the unit. In the first tape, you'll learn that there are 5 modes of operation: shutdown, startup, open loop, closed loop, and wide open throttle. As you may remember, the O2 sensor doesn't enter the picture until we get to closed loop operation. The reason for this is that only when the O2 sensor tip reaches 600 degrees can the O2 sensor start transferring information to the ECM. The way this works is that at 600 degrees, zirconia dioxide becomes an electrical conductor. It then starts transmitting data in the form of electrical voltages for the computer to read. The volts sent are based on how much oxygen the platinum coating on the sensor reads in the exhaust. The greater the difference between the outside, exhaust air, and the inside, constant air, the higher the output signal voltage. The smaller the difference between the exhaust air and the constant air, the smaller the output signal voltage. The O2 sensor operates at a voltage of between 1/10 and 9/10. Naturally, the amount of oxygen the sensor is reading is determined by the air-fuel mixture. We've already established that the ideal air-fuel ratio is 14.7 to 1. 14.7 to 1 is 45 hundredths of a volt to the ECM. A signal above 0.45 volts to the ECM indicates a rich mixture, a condition containing little or no oxygen. A signal below 0.45 reports a lean condition. The ECM responds to a rich condition signal with a lean command signal to the carburetor to lean out the mixture. A lean condition signal output is handled with a rich command signal by the ECM. As you can see, the command signal out is always just the opposite of the sensor condition signal in. If the computer consistently reads a signal about 0.45 volts, it will store a rich code, code 45. Consistently below 0.45, and it will store a lean code, code 44. In order for the computer to elect to store a code number, the vehicle must be running at cruise speeds for at least 5 minutes. However, this is only true for codes 44 and 45. A properly functioning O2 sensor will function from below the range of 0.35 volts to above 0.55 volts, back to the computer. If it never gets out of this range during a road test, you'll get a code 13 and a check engine light on the dash. It's important to note that getting a code doesn't necessarily mean there's a problem with the sensor, except in the case of code 13. That almost always indicates a bad sensor. We'll get more into codes and troubleshooting them in later tapes. Because the computer wants an air-fuel ratio of 14.7 to 1 for maximum efficiency, it keeps looking for a signal of 0.45 volts from the sensor. The signal is constantly fluctuating between 0.2 volts and 0.8 volts. And the ECM responds with output signals that attempt to hit the desired 0.45 volts, or 14.7 to 1 ratio. The oscillation would look something like this on a scope. A little above for a while, a little below for a while. It's sufficient to say that on a properly tuned car, it all averages out in the end. The following demonstration will give you an idea of how the O2 sensor works in the exhaust manifold. We'll get more into the actual working mechanics of the sensor in later tapes on diagnostic techniques. First, we'll hook up this 10 megohm digital voltmeter, a DVOM, to the sensor and pretend it's the ECM. As you may recall from science courses, the tip of a flame burns rich. That is, it uses up all the oxygen in the air. Placing the tip of the sensor into the flame, where there is little or no oxygen, we can see that the voltage goes up on the meter. Take the sensor out of the flame, into normal atmosphere, and the voltage goes down. Once again, into the flame, no O2, and the voltage goes up. Out of the flame, plenty of O2, and the voltage goes down. Don't forget, this is not a heat sensor. All the heat does is bring the sensor up to 600 degrees so it'll operate. Only then can the sensor measure the amount of oxygen in the air around it, just as it does in the manifold. Another extremely important sensor is the coolant temperature sensor. It plays a crucial role in startup and open loop modes. The coolant temperature sensor is the first sensor the ECM communicates with when you start your car on a cold morning. What the coolant temperature sensor does is provide the necessary control data to take you from the startup mode to open loop mode. It then directs the ECM as to when the system can switch to closed loop, where the O2 sensor becomes all important. The coolant temperature sensor also controls idle speed in a warm engine and activates a number of other output controls that we'll talk about later. The coolant temperature sensor operates on a full 5 volts of power, much higher than the O2 sensor. Located in the intake manifold near the thermostat, it's always on the hot side of the system to get an accurate temperature measurement. But the coolant temperature sensor is not simply a thermostat that opens or closes at a predetermined temperature. Instead, it's a very special type of resistor called a thermistor. The thermistor works in the opposite manner from a conventional resistor, the type you find in TV sets and many other everyday products, including automobiles. More specifically, in a conventional resistor, if you heat a copper wire, the resistance to flow of electrical current increases. But in the thermistor, the resistance increases the colder the unit gets. That's why the coolant temperature sensor on a cold engine has high resistance and delivers low voltage to the ECM. While on a warm engine, the resistance drops and the signal voltage increases. We can see how this works by hooking up an ohmmeter to the coolant temperature sensor. The sensor is somewhat warm at room temperature and resistance is low, signifying high signal voltage to the ECM. Using this freon to cool it, we see the resistance rise, which means much lower signal voltage to the computer. Warm it up again, and the resistance drops. The next input sensor we'll be covering is very important to the control of timing, converter clutch operation, and fuel control. It is the throttle position sensor. Basically, it's just another type of variable resistor and is located in the carburetor. On this GM unit, it is mounted in this position. To change the resistance of the switch, this pin is mechanically activated. The way this works is that a plunger under the accelerator pump arm moves the pin up and down in the switch. As we accelerate, the throttle linkage pushes the plunger down on the pin and changes the resistance of the switch. The ECM sends the throttle position sensor a 5-volt reference signal, and as you'd expect from a variable resistor, the resistance is high at idle speed, allowing a lower voltage to return to the ECM. Accelerate, and the plunger goes down. Resistance decreases, and the returning signal increases to a much higher voltage. To simplify matters, just remember, idle speed results in high resistance, low voltage signal to the ECM. Acceleration gives you low resistance, high signal voltage. And because the throttle position sensor is a variable resistor, the signal it returns to the ECM is constantly changing. Lower, higher, then lower again. The condition of the throttle position sensor is very important to the onboard computer for a couple of reasons. First, when the throttle position reaches 86% full, the ECM reads this information from the sensor and overrides the oxygen sensor. This allows the carburetor to provide a full rich mixture for extra power. Secondly, the throttle position sensor tells the ECM how you're driving. For example, let's say you just came over a steep hill, took your foot off the gas, and began to coast. The throttle position sensor would relay this information to the ECM, and it would unlock the torque converter clutch. Using an ohmmeter again, here's a demonstration of what actually happens as your foot goes up and down on the gas pedal. Connecting the throttle position sensor to the meter, we get a reading of 11,850 ohms. This is pretty high and means the ECM is getting back a low signal voltage. As we push the accelerator down, the resistance gets lower, the ohms drop, and we get a much higher voltage back to the ECM. The input data from the throttle position sensor tells the ECM two things. One, what the throttle position is, and two, how fast the position is changing. And that brings us to our next input sensor. For the moment, let's just call it a pressure sensor. There's a lot to explain about this sensor, so you want to pay extra close attention. The function of the pressure sensors is to provide manifold vacuum and barometric pressure data to the ECM. With this data, the ECM controls timing, converter clutch operation, and fuel mixture in open loop. There are three different types of pressure sensors. They look identical, and two of them perform the same function, but do so in different ways. To make things even more complicated, a few vehicles don't use any pressure sensors, while most will use one of the three, and some cars will use two of the three sensors. And to make matters worse, at replacement time, they are not interchangeable. There are two categories of pressure sensors for collecting data and getting it back to the ECM. The only difference between them is how the unit measures the pressure. One method is absolute pressure, the other is differential pressure. The ECM gets the same required input from either type, but can only correctly understand the type of unit specified in its PROM. Within these two categories, there are three types of pressure sensor units. All look pretty similar, as we just mentioned, and all have three wires. But they differ in that only two of the three types have vacuum hoses connected to them. The key element to the collection and reporting of pressure data is the diaphragm in the sensor unit. As the diaphragm flexes, it acts as a variable resistor to change the signal transmitted back to the ECM. The sensor also works on a 5-volt reference signal from the ECM. Under the category of absolute pressure sensors, we have the manifold absolute pressure sensor, commonly called the MAP sensor, and the barometric absolute sensor, or baro sensor for short. As you can see from the diagram, the resistance in both the MAP and baro sensor is being changed by the movement of the diaphragm against a fixed pressure, or atmosphere, in the unit. With the engine off, there will be virtually no resistance, and the unit will send a high signal voltage back to the computer. After we start the engine and begin to get some vacuum in the system, the resistance will increase, and the voltage going back to the ECM will drop. Vehicles using the absolute type of sensor will have either a MAP or baro sensor. In some cases, a vehicle may have both. In terms of resistance, there is one basic difference between the MAP and baro sensors. To move the diaphragm, the MAP sensor uses manifold pressure, and the baro sensor uses barometric pressure. This difference also explains why the MAP sensor has a vacuum hose connected to it and the baro sensor doesn't. The third type of pressure sensor is called a pressure differential sensor, usually called a vacuum sensor, or VAC for short. You'll see why in a minute. In the VAC sensor, The diaphragm flexes and changes resistance in the unit. This is based on pressure changes exerted by barometric pressure on one side, which is variable, and manifold vacuum on the other, which is also variable. The diaphragm sends the ECM signals that measure the differential between these two pressures. This type of unit also has 3 wires and a vacuum hose attached to it. The reason you can't replace a map sensor with a vac sensor, even though they both have vacuum hoses, is because they read the transmit signal data differently. If we add vacuum to the map and baro units, the signal voltage drops. But when we add vacuum to the vac sensor, the signal voltage increases. For a quick, practical demonstration, we'll attach the map sensor on our test engine to this digital volt-o-meter. Remember, with a map sensor, it's vacuum up, voltage down. With our map sensor connected, ignition on and engine off, the sensor reads high voltage. If this were a vac sensor, there'd be no voltage. We start the engine, develop some vacuum, and the voltage drops in the map sensor. On a vac-type sensor, the voltage would be increasing. On a baro sensor, we'd get the same readings as the map type. No vacuum, high voltage. Add vacuum, and the voltage drops. Because the vac sensor works just the opposite, you can't replace a map sensor with a vac sensor. In addition, there is a high-energy ignition sensor. This is the HEI module. It provides the ECM with input data on crankshaft position and RPMs in order to trigger the ignition system. We'll get more into this sensor later when we talk about outputs. The last input sensor we'll be examining is the vehicle speed sensor. The data from this sensor is used by the ECM in speed control and converter clutch operation control. This diagram gives you a pretty good look at the way it's put together. Inside the speedometer unit are 2 reflective blades, positioned 180 degrees apart. Mounted in the back of the unit is the sensor itself. It has a small light-emitting diode, an LED, and photocell built in. When the infrared light hits the reflective blade, it bounces back on the photocell. The photocell then transmits a weak impulse to an amplifier unit where it's stepped up to a higher input reference signal and sent back to the ECM. Because there are 2 blades 180 degrees apart that send back signals, the ECM measures the time between signals and converts this to the speed the vehicle is traveling. Well, that covers the most important input sensors. Of course, there can be many more depending on the make and model of the vehicle. This includes some for air conditioning, speed control, park neutral position, and brake switch, just to name a few. One thing is for sure, if it needs to be controlled, you can bet someday there will be an input sensor for it. In the next part of this tape, we'll look at output controls and see just what the ECM does with the data provided by the inputs.